Okay, Assalamu alaikum students. Welcome to another video lesson. Today we are talking about lesson 3, 1.3, which talks about acceleration. So what is acceleration? That is what we're going to find out today. So that's one of the learning objectives we're going to learn about. What is acceleration? And we're going to learn how to graph acceleration and what that looks like on a graph and how to analyze those graphs. So I'm going to start by reading this and then we're going to solve some problems. A small spider, less than 2 centimeters long, spots an insect. The spider crouches and crawls forward. Then it lifts its front legs and leaps, landing right on its victim. Amazingly, a jumping spider can jump 10 to 40 times its body length. That is a lot. To capture prey from very far away, it must accurately estimate its initial velocity. Once the spider jumps, the force of gravity controls its motion, causing it to follow a curved path. Okay? Its velocity changes at every point along the path until it lands on its prey. And before I answer this question here, I actually have a video I want to show you of what that spider looks like. It's pretty incredible, actually. Let's see if we can actually get this video to play. Here we go. It's amazing. Is that like a reaction video? Okay, you're watching this, and it's slow motion. It's called the jumping spider for a reason. SubhanAllah. I thought that was really cute. I love spiders. Um, they actually are not as nasty as people think. Anyway, write your answer to the question below. Think of a sport or activity in which the goal is to hit the target from far away. What are some of the challenges? So, I think the sport or the activity I can think of that's very, very common here is soccer or football. Okay. And what are the challenges from hitting the ball from far away? Is basically you got to think about if the goal is over here, and I'm trying my best to draw this. Okay, and the goalkeeper's in here, and you're trying to hit the ball from over here all the way onto the goal. You got to make sure that first of all you account for the curve because the ball is going to go down. You got to make sure that you hit it hard enough. You got to make sure that you're accurate enough. So there are a few things to bear in mind. The first one is the speed. You got to make sure that it's going to stay on its path and it's going to be going all the way to the goal, and it's not going to fall too early or it's going to go too hard and go over the goal. Second one is direction. You got to make sure that it's facing the right way, otherwise it would go over the goal or to the sides. And the third one I would say is you got to account for things like wind speed. You got to account for things like players along the way. So sometimes you might hit the ball on the side like that. Sometimes you might hit the ball straight. So it depends. So you got to look at all the different factors. Those are some of the challenges for sure. Oops. How come we are zoomed in? Let's see if we can do something about that. Here we go. Oh, back to this. Right, and we've watched this. Right, what is acceleration? So now we come to the bulk of the matter. What is acceleration? Suppose you're a passenger in a car stopped at a red light. When the light changes to green, the driver steps on the accelerator. As a result, the car speeds up or accelerates. In everyday language, accelerations mean the process of speeding up. So basically, that's when your speed changes. So if you go from 0 to 10 to 100 every time you're walking. If you're standing still and then you suddenly start walking, you're accelerating, okay? Because you're changing your speed. So simply put, acceleration equals change. Oops, I'm writing under the, oh, let me just move that out of the way so you can see. Acceleration equals change of speed. That's what acceleration is. Okay, we continue reading here. Acceleration has a more precise definition in science. Scientists define acceleration as the rate at which velocity changes. Okay, so velocity is even more accurate because it has a direction. So it's not just change in speed, it's change in velocity. Velocity, as we know, is speed with a direction. So change in velocity, as velocity changes from 0 to 10 to 20 to 30 to 40 to 100, then you're actually accelerating. And also acceleration can be negative, so you can actually have acceleration in the opposite direction, but we'll come to talk about that. Okay? So recall that velocity describes both speed and direction in an object. A change in velocity can involve change in both speed, direction, or both of those. In science, acceleration refers to increasing speed, decreasing speed, or changing in direction. So it's just the change in velocity. It doesn't have to be increasing. It doesn't have to be decreasing. It can also be change in direction. That's what acceleration refers to in science. And we'll come to understand this as we go on. Okay, let me put this back on top there. So here we have an example of changing speed. Okay. So whenever an object's speed changes, the object accelerates. Whenever its speed changes, it accelerates. So that means if it goes from 0 to 100, it's accelerating. But also if it's going from 100 to 0, it's accelerating. We call it deceleration. But it's the same. It's still acceleration. It's just changing speed. So that's, once you know that, then you know that anytime an object is changing its speed or changing its direction, it's accelerating. So let's say, for example, an object is moving this way. Oops, let's go back. In a straight line. Suddenly, it slows down, but then it speeds up again. That's acceleration because it has speed, it slowed down, and then it sped up. But what if the object continues moving at a constant speed? Then it's not changing its speed. Is it accelerating? No. But hang on a minute. It decides to change its direction. Then suddenly it's accelerating. So acceleration is either change in speed, whether it's speeding up or slowing down, or change in direction. Okay? Both of those are examples of acceleration. Okay, and here we have, sorry about the noise in the background, everybody's playing. And here we have an example of change in direction. Even an object that is traveling at a constant speed can be accelerating. How? We've just answered that. So basically, if an object is changing its direction, then we consider that acceleration. Because it's got to do with forces and it's got to do with external forces. You cannot accelerate without experiencing an unbalanced force. You can't change directions without experiencing an unbalanced force. It's literally Newton's laws of motion. So we're talking about the second law of motion specifically. But that's something you're going to encounter later on in physics. And so therefore acceleration is change in velocity or change in direction. Okay. Recall that acceleration can be change in direction as well as change in speed. Therefore, a car accelerates as it follows a gentle curve on the road or changes its lanes. Absolutely. So even if I'm going on the highway and I'm sticking to the road limit, let's say the highway says the speed limit is 120. Okay. And I'm going and I'm sticking to the speed limit. But however, if I look at the road looks like that. Okay, so the road looks like that. Now what this means is that the road is curving. So as I'm going along the road, I'm curving. What that means, I'm changing my direction. So I'm going north, but I'm forced to go slightly at an angle, slightly at an angle, slightly at an angle. And therefore, as I'm changing my direction, I'm actually accelerating. Even if my speedometer says 120, I'm actually accelerating because I'm changing direction. So, once again, changing velocity, slowing down, speeding up, or changing direction means accelerating. So let's have a look at this exercise over here. We've got an exercise that they want us to do. Acceleration during a game of soccer. A soccer ball, soccer is just another word for football. A soccer ball can show three types of acceleration: increasing speed, decreasing speed, or changing directions. So interpret the photos, label the type of acceleration that is occurring in each of the photos. So here's a ball that's still, that's stationary. Remember, stationary means it's not moving. A ball that is stationary, that is still, and then the guy suddenly kicks it. So it's going to start speeding up. It went from 0 to 30 meters per second, say. So what's that going to be? That's going to be speeding up. That's going to be accelerating by speeding up. So that's increasing speed. Increasing speed. So all three examples are acceleration, but we got to go and explore all of them. Here's another one. Here's another one. So this one we already said is increasing speed. I'm just going to write it again because it's a new slide. Increasing speed. What about this one here? What about this one here? So the ball was going and then the goalkeeper caught it. So the ball was coming towards the goalkeeper and he caught it, and so therefore it went from about 20 meters per second down to 0. So did the speed change? Yes, it is slowing down. So it's accelerating, but it's slowing down. And then over here we have a ball that's halfway midair, and then somebody gives it a header. So that's going to change its direction. So since it changed directions, even though the speed might have not changed, but the direction changed, we call that acceleration. So here we have changing direction. Very good. Let's move on. So how do we calculate acceleration? How do we calculate acceleration? Well, let's see. Here we have an airplane, what looks like a Cessna, one of those small planes. I've been in one before. They're kind of scary. Um, only because they're very, what's the word? Jittery. You have to balance them. Even as you go in, you got to make sure that the passengers are sitting in a way that's balanced, because it's quite a small plane and it's very turbulent. They can get, it can get a little bit unstable in there. But they're lovely planes. It's wonderful. Yeah. Hoping maybe one day I'll own one. Anyway, moving on. So predict. So we have a prediction to make, but before that, let me just read through this. Calculating acceleration. Acceleration describes the rate at which velocity changes. Describes the rate at which velocity changes. Okay, and so knowing that, if an object is not changing direction, you can describe its acceleration as the rate at which its speed changes. Okay, so if it's going in a straight line, then it doesn't have a direction, so the direction is the same. There's no change in direction. So the speed and the velocity are going to be identical. And so you can describe it as the rate at which speed changes. At your age, at this current level in grade 8, we are not so strict about that. However, when you go into high school, you'll have to know the difference between velocity and speed, and the difference between vectors and scalars, and the difference between an object that has a direction and one that doesn't. But for now, we can sort of assume that speed and velocity are very similar. It's just that velocity has a direction, obviously, and that it's a vector. Right, a vector quantity. If an object is not changing direction, you can describe its acceleration as the rate at which by which it changes its speed. To determine acceleration of an object moving in a straight line, you calculate the change in speed per unit time. So remember how we calculated velocity? Velocity is the change of distance over the change in time. So the total distance covered over time is speed or velocity. Now, with acceleration, it's change in speed over time. So not change in distance over time, which gives you speed, but it's rather change in speed over time. And how do we calculate it? Acceleration is very, very easy. Speed 2 minus speed 1 all over time. Now, there are different ways of writing this. You can write speed final minus speed initial, SF minus SI. You can also write um, velocity final minus velocity initial, which looks like this, VF minus VI over T, or change in T. And that just means it's the same thing, okay? And the triangle, you might have seen me draw triangles in the classroom when I'm talking about change in time or change in distance. That just means change. The triangle just means change, okay? So it's just an easy way of writing that. So basically when I'm saying change in speed over time, I can do this. Change in speed over time. Alternatively, I can write it like this, S2 minus S1, the final speed minus the initial speed, all over the time it took to change the speed. So if the speed is measured in meters per second, as is the case here, and the time is measured in seconds, the standard international unit for acceleration is meters per second per second. Okay, now why is that? Let me just explain it very quickly. The unit for speed is meters per second because it's distance over time. Now, if we are doing acceleration, then it's going to be speed over time, which means it's meters per second over seconds, which means it's meters per second, or meters per second squared. So you don't have to know how to get that. All you need to know is that acceleration has a unit of meters per second squared. Okay? And how do we calculate acceleration? We already determined that. So here we have an example. To calculate the acceleration of an airplane, you must first subtract the initial speed of 0 from its final speed of 24 and calculate the acceleration using the time. So let's have a look at this example. I'm going to do this one, and inshallah, the next one you'll be able to do yourselves. Right, so here we go. We have acceleration that we need to calculate. So acceleration is going to equal change in speed. So it's final speed, S2 minus S1, all over the time it took. Okay, that's how we calculate acceleration. Sorry. And what do we have here? What's the final speed? What's S2? Well, it's right here. 24 meters per second squared. Minus S1. What's S1? S1 is the initial speed, which is 0. Okay? Now, we don't have to calculate it from the initial speed. We might want to find the acceleration at this point, in which case this becomes S1. But if we want to find the acceleration throughout the whole journey, then we take S1 as the beginning speed, which is 0. Over the time, how long did it take for the plane to get to 24 meters per second? It took, right there, how long did it take? It took 3 seconds. So, and the answer is going to be 8 meters per second squared. I made a mistake here, guys, and nobody corrected me. What mistake did I make? I'll give you a second to think about it. What mistake did I make? The mistake I made was, I'm sure some of you figured it out, was over here. What's the unit for speed? Meters per second. It's not meters per second squared. The unit for acceleration is meters per second squared. Thank you for those of you that have yelled through your computer screen or your phone screen. Okay, let's have a look. So that is indeed the answer, 8 meters per second squared. And the airplane accelerates at a rate of 8 meters per second squared. What does that mean? So that means every second the speed is changing by 8 meters. Every second that plane's speed is increasing by 8 meters. So at 3 seconds it's going to be 32. I think it was 32, or is it 24? It was 24. And then if we give it another second, it's going to increase by 8, so it's going to be 32. And if we give it another second, the speed is going to be 40, and so on and so forth. So the plane accelerates at a rate of 8 meters per second. This means that the airplane speed increases by 8 meters per second every second. Every second it's increasing by that amount. Okay, so here they want us to do this. An airplane touches down on a runway with a speed of 70 meters per second. It decelerates at a rate of minus 5 meters per second. So here we have another scenario. We have a plane that is touching on the runway. I'm going to try and draw it in 3D. Okay, so here's the plane, and it's touching on this runway over here. Okay, now this plane is just coming down for a landing, and it's traveling at a speed of 70 meters per second. So that is S1. Okay, that is the initial speed, or VI. And what else do we have? Its speed is changing at a rate of 5 meters every second. So every single second, the speed of the plane is changing. Oh, sorry, I gotta move my face out of the way again. Let me try and do that. Here we go. So the speed is changing at a rate of 5 meters every second, and then it's telling you, can you predict what the speed of the plane is going to be after 1 second? 65? After 1 second, it loses 5 meters. That's what it means. The speed is going to decrease by 5 meters per second every second. After 2 seconds, it's going to be 60. After 3 seconds, it's going to be 55. After 4 seconds, it's going to be 50. And so you can actually, using that, you can determine when the plane is going to finally stop. How long is it going to take the plane to stop completely? Well, I can tell you right now, 14 seconds. How do I know that? 14 times 5 equals 70. So 14 times minus 5 equals minus 70. If we start off at 70, and to get to 0, then we have to, well, at a rate of minus 5 meters per second, it's going to take us 14 seconds. Simple as that. Okay, very, very simple stuff. Okay, and let's do this then. Ooh, here we have an example. Remember that plane, that Cessna plane I was talking about, the one I want to buy? Over here we've got an example of that we have to fill in. After 4 seconds, what is it going to be? Remember the change in this airplane was 8 meters every second. So after 4 seconds, when it was 24, at 3 seconds it was 24. And at 4 seconds it's going to add another 8, so it's going to be 24 plus 8, which is 32 meters per second. And what about, oh, let me move my face back up there. Oh, I keep doing this. My apologies. There we go. So what about after 5 seconds? After 5 seconds, it's going to be 32 plus 8, which is 40 meters per second. Okay, right. Let's do the maths. Calculate one type of ride. Oops, calculate. Oh, calculate one type of ride falls straight down for 3 seconds. During this time, the ride accelerates from a speed of 0 to a speed of 30 meters per second. What is the average acceleration for the ride? Well, the initial speed is 0. The final speed is 30 meters per second. And the time it takes is 3 seconds. So the acceleration is going to be S2 minus S1 all over time, which is going to be 30 minus 0 all over 3, or 10 meters per second squared. Don't forget the squared, we're talking about acceleration. Second question, a roller coaster accelerates from a speed of 4 meters per second to 22 meters per second. So the initial speed was 4, and the final speed was 22 meters per second, and the time it took was 3 seconds. So this time it's going to be, acceleration is going to be 18, which is 22 minus 4, because that's S2 minus S1, all over 3, oops, 18 over 3, which is going to equal, it's going to equal 6 meters per second squared. And that's how you do that. Okay, so that's the same one. So I might actually do it again here, sorry, because it was towards the end. So the initial speed was 4, and the final speed was 22, and the time it took was 3 seconds. So acceleration equals S2 minus S1 all over time, which equals 22 minus 4 all over 3, which equals 6 meters per second squared. Okay? Easy as that. And we've got some assessments of understanding. So define the rate at which velocity changes is called acceleration. Acceleration. Right. A softball has a what? Positive or negative acceleration when it is thrown. When it's thrown, it's increasing in speed. So if it's increasing, then it's a positive acceleration. That means it's moving up, it's increasing, it's adding on. A softball has a what acceleration when it's caught? When it's caught, it goes from about 30 meters per second or 20 meters per second to zero. So that means it's slowed down. So that's a negative acceleration. It's slowing down. C. Explain. A girl skates around the perimeter of a circular ice rink at a constant speed of 2 meters per second. Is the girl accelerating? So what she's doing is she's going around the circular ice rink and she is going at a constant speed. Her speed is not changing. 2 meters per second. 2 meters per second. Is she accelerating if the speed is not changing? Well, turns out she is. Why is that? Because her direction is changing. So here she's facing that way, and then here she's facing that way, and over here she's facing that way, and over here she's facing that way, and over here she's facing that way. So her direction's changing, and remember what we said, acceleration is changing speed or direction. So yes, because her direction is changing. Her direction is not constant, is changing. Okay. So now I know, let's see, now I get it. Yep. Now I know that in science, acceleration refers to change in velocity. And because it's change in velocity, it means change in speed or direction, or both. Okay, because velocity is speed and direction. Right, how do you graph acceleration? Suppose you bike down a long, steep hill. At the top of the hill, your speed is zero. As you start down the hill, your speed increases. As you start going down the hill, your speed increases. Each second you move at a greater speed and travel a greater distance than the second before. During the 5 seconds it takes you to reach the bottom of the hill, you are accelerating. You are an accelerating object. You can use both speed versus time graph and distance versus time graph to analyze the motion of an accelerating object. Yes, so we've talked about distance time graphs and I've shown you examples. So now we're doing speed time graphs and they're not much harder. Okay, they're just as easy. Let's have a look. So what are we going to put where? So with a speed versus time graph, once again, we always like to put time on the horizontal axis. So I'm going to put time over here, and the time depends on the graph. Over here is the graph data. So the time is going to be in seconds. And over here I've got the speed, and the units for speed is meters per second. And of course we always have a title. The title is going to be this versus this. So it's going to be speed versus time graph. And if you want to add a bit more detail, you can say for a hiker or a cyclist. So I think this one is for a cyclist. For a cyclist. It's very important that you always include the title so that people know what you are talking about. Okay, so what else do we have? We have 0 here because that's the point of origin. And then we have to decide on a scale. The speed goes up to 10. Speed goes up to 10. So I think a good scale would be 2, 4, 6, 8, 10. And then we've got 12. That's just for good measure. So we can actually predict things as well. What about the time? The time starts from 0 and then it goes to 1, 2, 3, 4, 5, and finally 6 seconds. So what happens now? What happens now is we simply plot the points. So I'm going to use a different colored pen. I'm going to use this light green color to plot the points. At 0, it was 0, so I'm going to draw just a single X here. And then at 1 second, the speed was 2. And at 2 seconds, the speed was 4. And at 3 seconds, the speed was 6. Oh, I can see a pattern here. And at 4, it was 8. And at 5 seconds, it was 10. And then if I want to, I can go back and draw a line of best fit. And I'm going to use orange. No, not orange. I'm colorblind. I hate orange. Orange and green together. I love green and I love orange. It's just that when they're together, I can't see them very well. Right, so let's see. So that is what a line of best fit looks like. Or what a, yeah, so basically the line for the graph is going to look like that. And it goes through all the points. And I can make a prediction that at 6 seconds, it's going to be 12, isn't it? Yeah, because it's basically double the time. So how do I calculate the speed? Acceleration is the same way I calculate speed. So it's going to be the gradient. The gradient of a speed time graph represents acceleration. The gradient or the slope of a distance time graph represents speed. Okay, so if it's distance time, it represents speed. That makes sense because speed is distance over time. Distance over time. And so if this is distance, this is time. Distance over time represents speed. Now with acceleration, sorry, my face is in the way. I keep forgetting. Nope. How do I capture my, oh, this way here. Nope, not that one, that one. Yep, I'm gonna take my face out of the way for a second. Over here is good. So that's speed. With acceleration, it's slightly different case. Obviously, it's acceleration equals speed over time. And so that graph is going to look like this, but this time we've got speed, not distance, and we've got time down here. And so the gradient, the slope, represents acceleration. That's all it is. Okay? Let's go to the next slide, and let's move my face back in the corner there where it belongs. Use the data to, here we have another set of data, and this one, whereas in the previous example, you can see that it's constant speed. The speed is not changing. Or, sorry, it's constant acceleration. Because it's changing by a set amount. But acceleration doesn't have to be constant. So what that means is it doesn't have to be changing at a rate of 2 meters every second or 3 meters every second. Sometimes it can be 0, sometimes it can be 2, 4, 6, 8, and increasing. So this is what we're going to experience over here by the looks of things. Distance versus time graph. So once again, we're asked to do this. Let's see if I can do it. I don't have rulers here, so I'm just going to try and wing it with using freehand drawing. Use the data to answer the questions. Graph this data to create a line graph. Plot time on the horizontal axis. Yeah, so we know all of that. So I'm going to use this as the y-axis starting point. And I'm going to use this as the x-axis starting point. Now I'm going to move around a bit because, as I said, I'm trying to do this on glass. Okay, that's as good as it's going to get. So let's have a look. I'm going to use blue now. Maybe purple. Purple. Is that purple? That's purple. Right, so that's 0. Time is over here, and time is going to be in seconds. How do I know? It's right there. Time in seconds. Distance is over here, and distance is going to be in meters. So what about the distance? The distance goes up to 25. So what would be a good unit? If it goes up to 25, it's a good thing to go in fives. So I'm going to go, that's 5, 10, 15, 20, 25. And for good measures, we'll go to 30. That's 30. Oh, that's annoying, that last one. No, please don't do that. Okay, fine, I'll do it again. And here we go. Do it right this time. There we go. That's 30. Now what about the time? The time goes to 5. only to 5. So I'm just going to go with 1, 2, 3, 4, 5, and then I'm just going to go to 6 here. 1, 2, 3, 4, 5, and 6 for good measures. And it's asking me to plot it. So at 0, it's 0. So what I'm going to do is I'm going to draw an X at 0. What about at 1? At 1, it's 1, 1, 1, as you can see. So at 1 second, it's 1. So it's over here somewhere. It's very, very down. At 2 seconds, it's 4. So it's about here. And then at 3 seconds, it's 9. Suddenly, it's shot up. So it's 3 seconds, it's about 9. I don't need that little dot over here. And at 4 seconds, it's 16, so it's really going up. And at 5 seconds, it is 25. So now we've got some sort of parabolic function. Okay, so there is what we're looking at here is a curved line. A curved line which tells us that there is an increasing speed. So the speed is not constant, but your speed is actually changing. And remember, this is distance time, whereas before it was speed time. So this is speed time. The first thing you have to remember is that this is speed versus time, and this is distance over time. So with a distance time graph that shows acceleration, it looks like a curve. With a distance time graph that shows deceleration, it looks like a curve in the opposite direction. So that's for distance time. With a velocity versus time graph or a speed versus time graph, it's going to show a straight line. Okay, so I'll come to explain that point. Might have to do a bit more, try and explain that point better. But basically with a distance time graph, if it's constant speed, then it's going to look like this. That's for constant speed. That's for speed that's not changing. But since the speed is changing, it's going to be a curve. An upwards curve if it's increasing or if it's speeding up. A downward curve if it's slowing down. Okay, that's for a distance time graph. Let's move on. Assess your understanding. Okay, I get it. Now I know that the two types of graphs that you can use to analyze motion of acceleration are, the two types of graphs are distance time, distance versus time, and speed versus time. Then you can use both of those. And that's the end of it. Thank you for watching, and I'll catch you on the next one, inshallah. Take care.